Hello, everyone. In this section, we will introduce reverse breakdown and capacitance characteristics of the p-n junction in electronics. As introduced in the previous section, the reverse bias current of a p-n junction is the saturation current, Is, as shown in the current voltage curve. Is is very small, only about 10 to the negative 18th to 10 to the negative 12th amperes. Therefore, under reverse bias, the p-n junction can be regarded as non-conducting. Under forward bias, the current increases exponentially with voltage. However, when the p-n junction operates under reverse bias, the reverse current seems to be a stable saturation current, Is, according to the equation. But when the reverse bias becomes very large, the current can also increase suddenly. As shown in the current voltage curve of the p-n junction, when the reverse bias voltage exceeds Vz, the current of the p-n junction rises sharply. This characteristic is called reverse breakdown. There are two main mechanisms for reverse breakdown in a p-n junction. First, we will introduce avalanche breakdown. The cause of avalanche breakdown is shown in the diagram. Let us zoom in on the space charge region. When a large enough reverse bias is applied to the p-n junction, the reverse electric field inside the space charge region becomes very strong. This strong electric field can break the covalent bonds in the semiconductor, allowing valence electrons to escape from the bonds and become free electrons in the conduction band. At the same time, an electron vacancy or hole appears in the covalent bond. Therefore, electron-hole pairs are generated inside the space charge region. The generated electron-hole pairs are then accelerated by the reverse electric field and gain high kinetic energy. They can collide with the silicon lattice atoms. In addition, during reverse bias, minority carriers that diffuse from the neutral region into the space charge region can also be accelerated by the reverse electric field, gain kinetic energy, and then collide with the lattice atoms. After high kinetic energy electrons and holes collide with the silicon lattice, they can again break covalent bonds and generate new electron-hole pairs. This behavior is called impact ionization. The newly generated electron-hole pairs, together with the original electron-hole pairs, continue to be accelerated by the strong reverse electric field inside the space charge region. They keep gaining high kinetic energy and continue to cause impact ionization. This snowball-like increase in electron-hole pairs is called the avalanche effect. Eventually, these generated electrons and holes move into the neutral regions of the p-n junction and form current. Therefore, this high current phenomenon under reverse bias is called avalanche breakdown. When avalanche breakdown occurs in a p-n junction, the atomic lattice has already been damaged by collisions, and this damage is irreversible. Besides avalanche breakdown, there is another mechanism that can increase reverse current. This is called Zener breakdown. Zener breakdown does not occur in every p-n junction. It mainly occurs when the doping concentrations on both sides of the p-n junction are very high, meaning that the acceptor concentration Na in the p-type semiconductor and the donor concentration Nd in the n-type semiconductor are both very high. When the doping concentration is high, as introduced in the previous section, the width of the space charge region becomes very narrow. At this time, the energy band diagram of the p-n junction is shown in the figure on the right. From the energy band diagram, we can see that the valence electrons in the valence band of the p-type semiconductor can undergo quantum tunneling between energy bands under a strong lateral electric field. As a result, electrons in the valence band of the p-type semiconductor tunnel into the conduction band of the n-type semiconductor, and then move into the neutral region to form current. The probability of quantum tunneling is strongly related to the tunneling distance. Only a very narrow distance can allow tunneling to occur. Therefore, Zener breakdown can occur only when both Na and Nd are high enough. The high current mechanism caused by this tunneling effect does not involve damage to the atomic structure. Therefore, it can be used repeatedly and is reproducible. After introducing reverse breakdown in the PN junction, we will next introduce the capacitance effect of the PN junction. First, let us define what capacitance is. From the mathematical equation, capacitance C is defined as the derivative of charge Q with respect to voltage V. This means that capacitance represents the change in charge caused by a unit change in voltage. Therefore, the key point of capacitance is how the amount of charge changes when the voltage changes. First, let us look at a PN junction under reverse bias, as shown in the figure on the right. Under the reverse bias VR, if we additionally apply a small signal bias, delta VR, what kind of charge will be affected? First, let us consider the space charge, which is also the junction charge introduced in the previous section. As introduced earlier, the amount of space charge shown here is proportional to the square root of V0 plus VR. V0 is the built-in potential and is independent of bias. From the equation, we can see that when the reverse bias VR increases to VR plus delta VR, the junction charge Qj increases. This is because the width of the space charge region becomes wider as the reverse bias increases. Therefore, under reverse bias, the change in space charge caused by a change in voltage is defined as the junction capacitance, Cj. Cj equals the derivative of Qj with respect to VR. The capacitance discussed here is the capacitance generated by an AC signal. It is the capacitance effect produced by applying an additional AC signal on top of a DC bias condition. Therefore, the capacitance calculated here is the junction capacitance obtained when the DC bias is operating at VR0 and an additional AC signal is applied. Thus, the junction capacitance Cj is the derivative of Qj with respect to VR under the condition VR equals VR0, as expressed by the equation on the slide. Next, we substitute Qj into the differentiation equation and take the derivative to obtain the equation shown on the slide. After properly rearranging the numerator and denominator, we can obtain a concise equation. The junction capacitance Cj equals the junction area A multiplied by the semiconductor permittivity, epsilon s, divided by the total width of the space charge region under the reverse bias VR0, WR0. This equation is exactly the same as the simplest parallel plate capacitance formula, C equals A times epsilon s divided by T. The only difference is that the insulator thickness in the parallel plate capacitor is replaced by the width of the space charge region. This conclusion is very important because it helps us understand the junction capacitance of a PN junction. Therefore, as the reverse bias increases, the space charge region becomes wider and the junction capacitance becomes smaller. Also, the space charge region exists even when there is no applied bias. Therefore, we can factor out the bias-dependent term in the space charge region width. As shown in the equation, WR0 can be written by factoring out W0, the space charge region width at zero bias, and multiplying it by the square root of 1 plus VR0 divided by V0. Therefore, under the reverse bias VR0, the junction capacitance can be written as the zero bias junction capacitance, Cj0, divided by the square root of 1 plus VR0 divided by V0. This clearly expresses the effect of reverse bias. It is also worth mentioning that the charge source of the junction capacitance in a PN junction is the change in space charge. This change in space charge still exists under forward bias. The only difference is that as the forward bias increases, the width of the space charge region becomes smaller. Therefore, we can also obtain the junction capacitance equation under forward bias. Under the forward bias VF0, the junction capacitance Cj equals Cj0 divided by the square root of 1 minus Vf0 divided by V0. Besides space charge changing with bias in a PN junction, are there any other types of charge that also change with bias? The answer is yes. We will use a PN junction operating under forward bias as an example. As shown in the figure on the right, when the PN junction operates under forward bias, the space charge region not only becomes narrower, but majority carriers are also injected across the space charge region into the other side. This causes a large increase in minority carriers in the neutral region. These minority carriers then diffuse and form transport current. As introduced in the previous section, the minority carrier concentration at the boundary between the neutral region and the space charge region has an exponential relationship with the applied bias, as shown in the equation. Therefore, under a DC forward bias VF0, if an AC signal delta VF is applied, the amount of minority carriers responsible for diffusion in the neutral region, called the diffusion charge QD, changes significantly. The capacitance effect caused by the change in diffusion charge is called diffusion capacitance, CD. It equals the derivative of the diffusion charge QD with respect to the forward bias, as shown in the equation on the slide. The diffusion charge QD can be written as the conduction current of the PN junction, IPN, multiplied by the transit time of the minority carriers inside the PN junction, tau t. Also, IPN equals IS multiplied by exponential of VF divided by VT minus 1. After substituting the diffusion charge QD into the equation, we can obtain that the diffusion capacitance CD equals tau t divided by VT multiplied by IPN. Since IPN has an exponential relationship with the forward bias, the diffusion capacitance CD also has an exponential relationship with the forward bias. What about diffusion capacitance under reverse bias? From the equation, because the PN junction current under reverse bias is the constant saturation current IS, after differentiation, the diffusion capacitance is almost zero. This means that under reverse bias, we do not need to consider this diffusion capacitance because its effect is almost negligible. From the carrier concentration plot on the right side of the slide, we can also see that the minority carrier concentration at the boundary between the neutral region and the space charge region decreases exponentially with reverse bias. When it becomes very low, the distribution no longer changes much. For example, the change from 0.001 to 0.0001 is 10 times in ratio. But from the perspective of differentiation, meaning the absolute difference, the change is only 0.0009, which is much smaller than 1 and can almost be ignored. Therefore, diffusion capacitance CD only needs to be considered under forward bias. To summarize the capacitance effect of a PN junction, under forward bias there are two types of capacitance: junction capacitance and diffusion capacitance. Under reverse bias, only junction capacitance needs to be considered. Therefore, the capacitance of a PN junction under forward bias is higher than that under reverse bias. That concludes the introduction to reverse breakdown and capacitance characteristics of the PN junction. Please look forward to the next class. See you next time. Bye-bye.